Salam sejahtera, my name is John Richard from Group 5 Section 3, Material Science. Today I will introduce about the magnesium aluminum alloy analysis with my group members. So first, in this assignment, we will analyze about the composition of magnesium aluminum alloy and several vintage of aluminium and focus on the product form after cool down by using phase diagram. Moreover, we will discuss about how to improve the material properties of magnesium aluminum alloy by several methods so that it will be more useful. And next is the physical property of magnesium, which is low ductility, higher bitterness, greater lightness, permeability, and for aluminium, it has high ductility, excellent malleability, good strength to weight ratio, high toughness. And next is the mechanical properties of magnesium and aluminium, which is at the density, melting point, electrical and thermal conductivity. Please take a look. And next is the important part, which is application of the magnesium aluminum alloy. So first, we will use it at transportation, at aerospace and automotive, as the magnesium and aluminium alloy have the lightweight so that it can support it. And next is used as the portable electronic because of its lightweight and also the high durability. And lastly, please take a look about the presentation of me and my group member at the composition analysis.
Hi everyone, I'm Aziza. So, today I'm going to walk you through the phase transformation of an magnesium aluminium alloy, specifically one with 5% aluminium and 75 magnesium, as it cools down from a completely liquid state to room temperature. First, when the alloy is heated above 624 degrees Celsius, it's completely liquid. There's no solid at all, just a uniform molten mixture. As we cool below 624 degrees Celsius, alpha solid solution starts to form. At this point, we have two phases coexisting, solid and liquid. The solid fraction slowly increases as the temperature drops. Continuing to cool, the solid grains grow larger and more of the liquid turns into solid. We are still in a two phases region here, where solid alpha plus liquid. Eventually, all the liquid solidifies. The structure is now fully solid and consists of only one phases, an alpha solid solution. Finally, when we cool below 275 degrees Celsius, an intermetallic compound called aluminium 12 magnesium 17 precipitates out within the solid grains. This happens inside the already solid structure. Now, if you look at the phase diagram at 610 degrees Celsius for our 5% aluminium alloy, we can do a quick level rule calculation. The solid composition is 2.5% aluminium and the liquid is 8% aluminium. That gives us about 45.45% solid and 54.55% liquid at that temperature.
Hi, Assalamualaikum. My name is Muhammad Al-Asri. So today I want to explain about the solidification behavior of the magnesium aluminium that contain 20% of aluminium alloy. So this is our phase diagram. So there's a 5 phase. In the first phase, there's a liquid state, and the second state, the alpha solid solution start to form and the solidification start to begin. In the third phase, the alpha solid is grown into the large grain, and then the fourth phase, all the liquid has solidified and the lamella alpha plus Al12 Mg17 and start to form. And the final phase, the lamella structure is fully grown. So this is our cooling curve. So at the beginning of the cooling curve, magnesium aluminum that contain 20% of aluminium is completely at the liquid state. As the temperature decreases smoothly with time, until it reaches the 598 degrees Celsius, the solidification start to begin, and also the solid solution start to form from liquid. As the cooling continues until reach the 437 degrees Celsius, the thermal arrest appear on the cooling curve. So the 3 to 4 is the process cooling. So this is a phase condition for 20% of aluminium. So for the alpha, we have 64.71%, and then we have 35.29% of Al12 Mg17.
Hi everyone, I'm Sona Grace and today I am breaking down the science behind a special magnesium aluminium alloy, specifically one containing 33 weight percent aluminium. If we look at the magnesium aluminium phase diagram, the 33% aluminium composition is extra interesting. This is because it passes right through a point called the eutectic. At 437 degrees Celsius, a eutectic reaction occurs. That's when a single liquid transforms simultaneously into two different solid phases. In our case, it is liquid transforming into magnesium to aluminium 12 and Mg17. Now, let's walk through what happens step by step. Up here, above 437 degrees Celsius, it's all liquid, 100% molten alloy. Right at the eutectic temperature, the liquid can't stay liquid anymore. It doesn't freeze into one solid, but instead it transforms into two solids at the same time. This is the eutectic reaction. As it cools down just below 437 degrees Celsius, these two solid phases grow together in an alternating lamellar structure. Think of it like layer strips, one phase of magnesium next to one phase of Al12 Mg17 repeating over and over. Okay, so we now know what happens at the eutectic point, but how do we actually see it happening? Well, that's where the cooling curves comes in. It's like the alloy's heartbeat monitor as it solidifies. Let's track our 33% alloy as it cools down. Now, as can be seen here on the screen, at first it's all liquid and the temperature drops steadily, so the line slopes down smoothly. But right at 437 degrees Celsius, something changes. The temperature stops dropping for a while, and this flat zone is the eutectic halt. Why does it pause? Well, it's because during this time, energy is being released as the liquid transforms into two solids. That latent heat keeps the temperature constant until the reaction is complete. Now, once all the liquid has turned into that fine lamellar structures like what we talked before, the temperature starts falling again, now as a fully solid material. So there you have it, from liquid to layered solids, all captured in one cooling curve. We followed the cooling curve and seen the eutectic reaction at 437 degrees Celsius. Now, let's fast forward down to 225 degrees Celsius and see what our 33 weight percentage aluminum alloy looks like once it's completely solid and cooled further. At this lower temperature, our alloy isn't just one thing. It is a mix of two solid phases, alpha magnesium, which at 225 degrees Celsius contain about 5% magnesium and 95% aluminium. Yes, it's mostly aluminium in solid solutions. And at aluminium magnesium, an intermetallic phase with roughly 43% magnesium and 57% aluminium. These aren't random guesses. They come straight from the phase diagram solubility limits at this temperature. Now, how much of each phase do we actually have? That's where the lever rules comes in, and after we apply the lever rule like we seen here in the screen, we will get this value.
Assalamualaikum. So I will continue solidification of 40% with H aluminium. This slide explains how liquid mixture of 40% aluminium transform into a solid as the temperature drops. For the first phase, we begin at a high temperature where the material is completely in a uniform, which is liquid phase. Beginning of solidification, as we hit the liquidus line, the first solid crystal known as primary Al12 Mg17 begin to form with the liquid. At the third phase, as cooling continue, the primary solid aluminium 12 magnesium 17 crystals grow larger, taking up more space in the mixture. In the eutectic transforms, once we reach the eutectic temperature, the remaining liquid transform into a lamellar structure. For final microstructure, the solidification is now complete. The final metal consists of large primary aluminium 12 magnesium 17 crystals surrounded by a fine strap lamellar background. So for the second slide, we will show the cooling curve and the phase composition. For the cooling curve, the graph on the left show how the temperature stays constant during the eutectic reaction, which is the flat line from point 2 to 3, which is where the lamellar structure form. For the phase composition analysis on the right, we use the lever rule to calculate the percentage of different solid present at 225 degrees Celsius for our 40% aluminium alloy. To calculating weight alpha by looking at the distance between the phase boundaries at 5% and 43% aluminium, we find that the mixture contains approximately 7.89% of the composition alpha phase. To calculating weight beta using the same method, we find that the majority of the material, about 92.11%, has transformed into a composition beta phase. For summary, this calculation proves that at room temperature, this specific alloy is mostly made of all of the aluminium 12 magnesium 70 compound with only a small amount of magnesium solid solution. That's all from me.
Salam sejahtera, my name is John Richard from Group 5, Section 3, Material Science. And now I would like to introduce about the solidification of 60% weightage of aluminium in magnesium aluminum alloy. So, you can see at the figures, at phase 1, there is only liquid magnesium aluminum mixture above 437 degrees Celsius. After that, at phase 2, the liquefaction will start occurs at 437 degrees Celsius and the primary of trialuminium dimagnesium will form. After that, at phase 3, all of the remaining liquid solidifies into laminar structure of trialuminium dimagnesium and FCC of aluminium. After the cooling down, at phase 2, the microstructure is unstable in this composition and temperature, and some of the FCC of aluminium will react with trialuminium dimagnesium and form aluminium 30, magnesium 33. After that, at phase 5, after passing through the 250 degrees Celsius Utah line, the aluminium 30, magnesium 23 will decompose and form secondary laminar structure of aluminium 12, magnesium 17, and trialuminium dimagnesium. So now let's look at the cooling curve. At the cooling curve, the magnesium aluminium liquid will start cooling and solidifies at 437 degrees Celsius when all of the liquid solidifies to trialuminium dimagnesium and FCC of aluminium. Some of the FCC of aluminium will react with trialuminium dimagnesium and form aluminium 30, magnesium 23 at temperature between 420 degrees Celsius to 250 degrees Celsius, as it is not stable at this composition and temperature. Lastly, all of the aluminium 30, magnesium 23 will transform to aluminium 12, magnesium 17, and trialuminium dimagnesium of laminar structure and cool down until room temperature. And now, let's look at the phase composition. So, I will take the temperature at 300 degrees Celsius. So, the phase present at here is aluminium 30, magnesium 23, and trialuminium dimagnesium. So, at this temperature, the composition of aluminium 30, magnesium 12 is 58% of aluminium and 42% of magnesium, where the composition of trialuminium dimagnesium is 64% of aluminium and 36% of magnesium. So, after we calculated by using Liber rule, the amount of aluminium 30, magnesium 12 is 66.67%, while the amount of trialuminium dimagnesium is 33.33%. That's all from me. Thank you.
Now, how do we make it stronger? First, let's play a grain size game. In a material with large grains, defects can travel long distances easily. That is weakness. But when we refine the grams, make them super small, we create a crowded highway. Every grain boundaries act like a roadblock, stopping those defects in their tracks. This grain boundary strengthening is a fundamental way to toughen up any metal, improving fatigue life and making it more uniform. Trick number 2 happens at the atomic level. This is solid solution strengthening. When we add aluminium to magnesium, this aluminium atom substitutes into the magnesium crystal lattice. But that's the catch. There are different sizes. This size difference creates atomic level strength, a distorted landscape. When a defect tries to glide through, it's like trying to run across a trampoline with other people on it. It gets slowed down and trapped. More obstruction means more strength and hardness.
Now that we understand how the magnesium aluminium alloy solidifies, let's talk about how we can make it even better. There are two other main ways to improve this material: by adding other elements and by refining its grain structure. The base magnesium aluminium alloy already has the aluminium 12 magnesium 17 intermetallic phase, but we can add more things to strengthen it further and improve corrosion resistance. Adding silicon make it easier to cast and can improve wear resistance. Adding copper can boost its strength without hurting corrosion resistance too much. It can also help reduce something called stress corrosion cracking. These are just small deliberate changes to the chemistry to get the properties we want. This is about changing the physical structure or the grain size inside the metal. Using grain refiners, we can add tiny amounts of element like titanium or zirconium. These act like seeds, giving the solid more places to start growing from during cooling. And smaller grains generally mean a stronger and tougher metal. Cold working. This means mechanically deforming the solid metal like rolling or hammering it at a low temperature. This process breaks up and stretches the grains, making the structure finer and more tangled, which increases strength and hardness. So, by carefully choosing additional elements and by controlling the grain size through refinement or cold working, we can tailor this magnesium aluminium alloy to be stronger, tougher, and more resistant to corrosion for specific applications. And that's a quick look at improving the material.
For the conclusion, MDAL alloy are widely used in automotive and aerospace applications due to their low density and good mechanical properties. The study analyzed the effect of aluminum contents on phase formation using the MDL phase diagram and showed the strengthening mainly occur to grain boundary strengthening and substitutional solution strengthening, which restrict the solution movement in the alpha MEMD matrix. In addition, alloying elements such as silicon, copper, and zinc improve the stability strength with resistance and corrosion behavior, while grain refinement using titanium and zirconium and cold working for the enhanced strength and hardness, making MDA alloy suitable for lightweight and structural application. So thank you so much for watching our video, and don't forget to like and subscribe. Bye bye.